Deep within the silence of space, a signal pulses from a dying star. These are not the predictable rhythms of normal stellar activity. They are anomalies, 25 distinct and unexplained transmissions coming from ancient red giants, each one a cosmic mystery waiting to be solved. By the end of this, you will know the full, eerie catalogue of signals that challenge everything we think we know about the final years of stars. Some patterns are so precise they seem engineered, while others burst forth with chaotic energy that defies all prediction. What message might the universe be sending us from its oldest, most brilliant beacons? The first signal on our list comes from a star you can see with your own eyes on a clear winter night. Betelgeuse, the fiery red shoulder of the constellation Orion, sent a burst that made astronomers question their most fundamental models. This was not a slow, predictable pulse. It was a powerful, intermittent radio transmission, a sudden shout in a frequency band where a dying supergiant should be relatively quiet. The pattern was the real mystery. It was not random stellar noise, nor did it match the rhythmic oscillations of typical stellar activity. Instead, it arrived in clusters with a strange cadence that seemed to defy natural explanation. One theory suggests it could be the sound of massive, previously unseen convection cells churning deep within the star's final struggles. Another, more speculative idea points to the possibility of complex magnetic field interactions, a cosmic dynamo of unimaginable scale behaving in a way we have never witnessed. The most profound question, however, lingers in the silence between these bursts. Could such a precise and powerful pattern be the product of an entirely unknown natural phenomenon, or does it hint at something more deliberate, a signal not just from a star, but from something using the star as its beacon? That strange cadence from Betelgeuse has led scientists down two fascinating paths. The first theory involves colossal stellar flares, far beyond anything our own sun could produce. Imagine the entire surface of a star suddenly convulsing, releasing a tsunami of energy that ripples across space as a radio shout. This could explain the burst's power, but the clustered pattern, the way the signals group together, remains a puzzle. A second, equally compelling idea suggests a hidden dance partner. Perhaps Betelgeuse is not alone. A small, dense companion object, like a neutron star or a black hole, could be orbiting unseen, its immense gravity periodically tugging at the star's outer layers. This gravitational interaction might rip material away, creating violent, predictable disturbances that we detect as those intermittent radio pulses. The implications of these natural explanations are staggering enough, rewriting our understanding of how supergiants die, but the most profound question still hangs in the air. What if, against all odds, the signal was not natural? The very notion challenges our place in the cosmos. A deliberately engineered transmission from a star like Betelgeuse would imply an intelligence not just existing, but operating on a scale we can barely comprehend. They would be using the star itself as a lighthouse, a cosmic amplifier for a message meant to last for eons. It would mean the universe is not just old, but deeply, anciently inhabited. While the scientific consensus firmly leans toward a natural, if extraordinary, cause, the mere possibility forces us to look at the night sky not as a collection of objects, but as a potential neighborhood. Antares, the rival of Mars glowing in the heart of Scorpius, broadcasts a melody. This is the second signal, a phenomenon so ordered it feels composed. While Betelgeuse shouted in erratic bursts, Antares sings with a low, persistent hum, a harmonic resonance that repeats with mathematical precision. For a star in its volatile red giant phase, this consistency is deeply unnatural. A star this old and unstable should be a cacophony of random energy releases, its surface a churning ocean of plasma. Instead, astronomers detect a clean, repeating frequency, a steady pulse that defies the chaotic death throes expected from such a colossal object. It is as if a giant bell were ringing in the void, its tone unwavering against the stellar storm. This precise rhythm has made it a prime candidate for SETI, the search for extraterrestrial intelligence, precisely because its pattern is so hard to explain through conventional astrophysics. Natural stellar oscillations, known as asteroseismology, do create rhythms, but they are complex and ever-changing, like the many sounds of a shaking building. The signal from Antares is different. It is a single, pure tone that persists, a beacon of order within a maelstrom of chaos. The most logical natural explanation points to a resonant cavity within the star's own atmosphere, a region where trapped magnetic waves could, in theory, amplify one specific frequency. Yet even this elegant idea struggles to account for the signal's remarkable stability over time. The haunting alternative is that we are not listening to the star itself, but to something superimposed upon it. A technologically advanced civilization might use a star's immense energy to power a transmitter, a lighthouse whose beam is so constant it appears to be a natural part of the celestial body. This harmonic from Antares does not just ask what a star is, but what it could be used for. This strange cosmic melody from Antares is a puzzle of order, but our third signal presents the exact opposite problem. It comes from a star named Mira, the wonderful, a variable star in the constellation Cetus. For centuries, astronomers have watched Mira rhythmically brighten and dim in a cycle lasting about 330 days, a predictable heartbeat in the sky. Yet recently, we have caught it in a series of lies. Mira has begun producing sudden, erratic pulses of energy, ultra-bright flashes that appear completely at random, completely disconnected from its well-documented pulsation cycle. It is as if a steady, rhythmic drumbeat were suddenly interrupted by unpredictable crashes of thunder. These are not minor fluctuations. These flashes are incredibly powerful, and they pose a direct challenge to our models of how aging stars like Mira behave. We thought we understood Mira's final act. It is a star slowly dying, pulsating as it sheds its outer layers into space, creating a beautiful, trailing comet-like tail. These new, rogue bursts suggest something far more violent and chaotic is happening deep within its core. One possibility is that we are witnessing the death of a planet. As Mira expands, it could be consuming a previously unknown planetary system. The violent disintegration of a gas giant or a rocky world falling into the star would release a titanic flash of energy, a stellar indigestion that we see as one of these ultra-bright pulses. Another theory points to instabilities in the star's own nuclear fusion furnace. The process of burning helium in a shell around an inert carbon core is inherently unstable, and perhaps we are seeing that instability manifest in these sudden, catastrophic energy releases. These erratic signals force us to reconsider the final years of a star's life. It may not be a gentle, predictable fade, but a series of violent, unpredictable fits and starts, a dramatic and chaotic finale we are only just beginning to decode. The erratic death throes of Mira show a star in chaos, but our next mystery reveals a strange synchronicity in the night sky. Two separate signals, both emanating from the constellation Gemini, present a puzzle of cosmic coordination. First is the Pollux pulse. From the star Pollux, a gentle giant that should be in its quiet old age, we detect a series of rapid, high-energy bursts. These are not the slow, grand pulsations of a typical variable star. They are sharp, staccato flashes, like a frantic heartbeat from a celestial body that should be calm and steady. Each burst is incredibly powerful, yet they arrive in a tight, rapid-fire sequence that lasts only moments before the star returns to its serene appearance. It is as if something is causing the star to fire a quick, intense volley of energy into the void. Then, from its celestial twin, comes an even more perplexing signal. The Castor code originates not from a single star, but from the complex Castor system, a sextuplet star system bound in a dizzying gravitational dance. The signal from this stellar maze is not a simple pulse. It possesses a complex, almost algorithmic structure. It is a pattern within a pattern, a sequence of frequencies and pauses that repeats in a way that feels less like a natural phenomenon and more like a structured message or a sophisticated beacon. One signal is a frantic shout, the other a complex whisper. The Pollux pulse is raw, explosive energy, while the Castor code is intricate and layered with information. What connects them beyond their shared constellation is the profound mystery of their origin. How can a single, aging star like Pollux produce such violent, focused bursts? And what natural process in the chaotic ballet of 6 stars could possibly generate a signal with such a logical, repeating architecture? The most tantalizing possibility is that we are not looking at 2 separate anomalies, but 2 pieces of a single, larger puzzle, a conversation happening in our own galactic backyard that we are only just beginning to overhear. Aldebaran, the fiery red eye of the Taurus constellation, holds a secret that echoes across the light years. This is the 6th signal, and it defies all expectations of how a stellar transmission should end. While other stars send sharp bursts or rhythmic pulses, Aldebaran emits a long, drawn-out radio echo that can persist for hours after the initial event. It is not a quick shout, but a sustained whisper that lingers in the void, a spectral fingerprint that refuses to fade. The signal's unique properties are what truly baffle scientists. Its spectral signature, the specific combination of frequencies it contains, is unlike any known natural stellar emission. It is a complex, almost mournful sound that carries the imprint of something vast and unseen surrounding the star. So what could cause a dying giant to ring like a bell for such an impossibly long time? One compelling theory points to a previously undetected debris disk. Imagine a colossal ring of dust, rock, and ice, remnants of a planetary system that was torn apart as Aldebaran expanded into its giant phase. When the star itself emits a burst of energy, that energy slams into this immense disk. The disk does not absorb it quietly. Instead, it acts like a cosmic amplifier and reverberator, catching the initial signal and bouncing it back and forth between countless particles. This chaotic chorus of reflections would stretch a brief pulse into the long, lingering echo we detect, transforming a stellar event into an hours-long symphony of scattered light and radio waves. Another, more exotic theory suggests an immense magnetic field interaction. Aldebaran could possess a magnetic field of unimaginable complexity, a tangled web of force that traps the energy from a flare. Instead of being released all at once, the energy is slowly siphoned away, leaking into space over hours like water seeping from a fractured dam. This process would create that drawn-out, fading signature, a natural magnetic prison slowly releasing its captive energy. Both explanations paint a picture of a star system far more dynamic and structured than we ever imagined. Yet the echo's persistence challenges even these ideas, leaving us to wonder if we are hearing the death rattle of a world or the resonant hum of a machine we have not yet learned to recognize. Just as one signal fades into a lingering echo, another flickers into existence with maddening inconsistency. From the variable star Leonis comes our 7th cosmic puzzle, a transmission defined by its elusiveness. This signal does not build or fade, it simply blinks on and off, appearing without warning and vanishing just as suddenly. For astronomers, it is a ghost in the machine, a pattern of light and radio waves that is here one moment and gone the next, leaving only empty data streams in its wake. This transient nature makes it nearly impossible to study, as you can never predict when it will show itself again. The very unpredictability is the heart of the mystery. Why would a star produce such a sporadic and powerful signal? The most compelling theory points to sporadic, cataclysmic events ripping across the star's surface. Picture titanic stellar flares, but on a scale so immense they make our sun's outbursts look like mere sparks. These are not steady processes, but singular, violent explosions. A massive buildup of magnetic energy deep within the star could suddenly snap, releasing a focused beam of radiation so intense we can detect it across the vastness of space. The signal flashes into our view for the brief duration of this cosmic detonation, and then it is gone, the star returning to its normal state as if nothing happened. Another possibility involves the star-consuming asteroidal or cometary material. As our Leonis pulsates and sheds its outer layers, a large asteroid or a swarm of comets could be pulled into a fatal dive. The violent disintegration of such a body against the star's photosphere would create a brilliant, short-lived flash of emission, a final scream of light and energy that we capture as one of these fleeting signals. Each disappearance of the R. Leonis riddle is not an end, but a pause, a silent promise that another cataclysm will eventually occur. It forces us to ask what other violent, hidden dramas are playing out on the surfaces of these ancient stars, events we only glimpse in their most fleeting and explosive moments. While the R. Leonis signal flickers with chaotic inconsistency, our eighth mystery presents a stark contrast of perfect order. Rasalgethi, a brilliant red giant in the constellation Hercules, emits a sequence of pulses so precise they could be set to a cosmic clock. This is not the erratic bursting of a dying star, but a steady, repeating pattern, a metronome ticking in the void with unwavering regularity. For a star in the turbulent, expanding phase of a red giant, this clockwork behavior is deeply unnatural. These stars are massive, churning cauldrons of plasma, their surfaces roiling with immense convection cells and their energy output fluctuating wildly. A stable, periodic signal emerging from such chaos defies our basic understanding of stellar physics. It suggests a source that is somehow insulated from the stellar turmoil, a mechanism that operates with cold, mechanical precision. One compelling theory points to the ghost of a planetary system. Imagine a dense, solid core of a gas giant planet, a world that somehow survived the star's violent expansion. This planetary remnant, a blackened cinder of metal and rock, could be locked in a tight, rapid orbit around Rasalgethi. As it whips through the star's intense magnetic field, it might act like a dynamo, generating a focused beam of radio energy with each pass. The orbit itself would provide the impeccable timing, a natural clock producing the repeating sequence we observe. Yet the sheer power and clarity of the signal challenge even this elegant explanation. The more speculative and profoundly more exciting possibility is that we are detecting a technosignature. An advanced civilization might establish a beacon in such a system, using the star's vast energy to power a transmitter that pulses with mathematical regularity. This would not be a message in content, but in form, a simple, repeating pattern designed to catch the attention of any species that understands the language of mathematics and physics. It is a cosmic handshake, a way of saying we are here and we understand the universe operates by rules. The Rasalgethi sequence forces us to ask a fundamental question. Where do we draw the line between a bizarre yet natural celestial phenomenon and the deliberate fingerprint of intelligence? In the search for cosmic company, a perfect repeating pulse might be the most compelling clue of all. The perfect rhythm of Rasalgethi's metronome gives way to a signal that seems to break its own rules. From the southern star Gacrux comes a transmission that stutters and jumps, a phenomenon astronomers call the Gacrux glitch. This signal does not pulse or fade. It abruptly skips frequencies, vanishing from one radio band only to instantly reappear in another. It is a cosmic broadcast that acts like a malfunctioning transmitter, hopping across the dial as if controlled by a faulty switch. This bizarre frequency hopping is the core of the mystery. Natural stellar emissions do not behave this way. A solar flare or a convective outburst might peak and fall across a range of frequencies, but it does not execute clean, instantaneous jumps from one discrete band to a completely different one. The Gacrux glitch does exactly that, creating a pattern that feels less like a natural event and more like a piece of sophisticated technology suffering an intermittent error. The scientific debate is sharply divided. One camp points to a highly unusual plasma effect within the star's immense atmosphere. Gacrux is a red giant with a complex, layered structure. Theorists suggest that powerful magnetic shocks could be traveling through different layers of plasma, each with its own unique density and electrical properties. As a shock wave hits a boundary between these layers, it could theoretically cause the emitted radiation to suddenly shift to a new frequency, creating the illusion of a glitch. It would be akin to a sound wave moving from air into water, changing its character instantly. This is a compelling natural explanation, but it requires a set of stellar conditions so precise and unstable that many researchers find it difficult to accept. The other, far more speculative side of the debate cannot ignore the unnerving resemblance to human technology. We build frequency hopping systems for our own communications, specifically to avoid interference and enhance security. The glitch from Gacrux mimics this principle on a stellar scale. Could we be witnessing an ancient beacon, a piece of astro-engineering so old that its mechanisms are beginning to fail, causing these erratic jumps? Or perhaps the glitches are not a sign of failure at all, but part of the message's complex structure, a code written not in the signal itself, but in the pattern of its delivery. The Gacrux glitch forces a difficult question. When we look for signs of intelligence in the cosmos, are we searching for perfect order, or are we also listening for the telltale imperfections of a machine? The steady malfunction of Gacrux is replaced by a signal of bewildering complexity from one of our nearest stellar neighbors. Arcturus, that brilliant orange beacon in the northern sky, emits a transmission that seems to contain two contradictory voices at once. This is the Arcturus anomaly, a broad, chaotic radio roar that hides within it sharp, whisper-thin signals, like finding a perfectly tuned flute playing a clear melody inside the heart of a hurricane. The discovery of this mixed signal dates back to the early days of radio astronomy, but its true nature has only become clear with modern, sensitive equipment. For decades, astronomers dismissed the broad-spectrum emission as simple stellar noise, the expected radio static from the star's churning atmosphere. It was only when they looked closer that they found the narrow-band spikes embedded within the noise, precise frequencies that stood out with unnatural clarity. This combination is what makes the anomaly so deeply perplexing. A star like Arcturus should produce one type of signal or the other, not both simultaneously from what appears to be the same source. The broad-spectrum roar is the sound of raw thermal energy, the immense heat of the star's outer layers, but the narrow-band components are different. They are the signature of non-thermal processes, the kind of focused, coherent energy produced by masers or by structured magnetic fields. It is as if the star itself is speaking in two different languages at the same time, one a primal scream and the other a precise technical code. So what could possibly explain this duality? One compelling theory suggests we are witnessing the violent interaction between Arcturus and a previously unknown Jupiter-sized planet. The star's powerful magnetic field could be funneling charged particles from its atmosphere onto the magnetic poles of this close-orbiting giant. This immense, continuous interaction would create the broad, roaring background static. Meanwhile, the planet's own magnetosphere, whipping through this stellar wind, could act as a natural amplifier, generating the sharp, narrow-band maser emissions we detect within the storm. Another, more radical idea posits that Arcturus is not one phenomenon but two, perhaps a dense, energetic companion like a white dwarf or a neutron star is orbiting Arcturus hidden from our view. The red giant provides the chaotic, broad-spectrum backdrop, while its invisible partner generates the precise, narrow-band signals through its own intense magnetic processes. This would mean we are not looking at a single star, but at a complex binary system, a cosmic duet creating a signal of unparalleled strangeness. The Arcturus anomaly challenges our very definition of a star. It forces us to ask if what we see as a single point of light is in reality a stage for multiple, overlapping cosmic dramas, a place where nature's forces collide to create a transmission of beautiful and inexplicable complexity. Far to the north, the constellation Cygnus presents a pair of mysteries that seem to speak to one another. The first is the Satyr signal emanating from the star at the heart of the celestial swan. This is not a diffuse emission or a gentle pulse. The energy from Satyr arrives as a series of intensely focused beams, like a cosmic laser pointer aimed with astonishing precision. For a red supergiant, a star whose atmosphere is a turbulent, chaotic soup of plasma, generating such a coherent, narrow beam is nearly impossible. It suggests a source that is not the entire star, but a specific, incredibly active region on its surface or in its immediate vicinity. The power behind these beams is staggering, channeling the star's raw energy into a tight, directed stream that punches through the interstellar medium. One natural explanation points to a stellar flare of unparalleled magnitude, but one that is somehow funneled and focused by an immensely powerful, localized magnetic field. Picture a wildfire hose compared to a sprinkler. The Satyr signal is the hose, concentrating a star's fury into a needle-thin jet of radiation. Yet, the consistency and focus of these beams challenge even this dramatic idea, leaving astronomers to wonder what kind of stellar phenomenon could possibly act as such a perfect natural lens. The second Cygnus conundrum, the Deneb echo, provides a possible and even more bizarre answer. From the brilliant supergiant Deneb at the swan's tail, we detect a signal that feels strangely familiar. Its spectral signature, the unique combination of frequencies it emits, does not appear to be original. Instead, it bears a striking resemblance to other known cosmic events, including the very beams from Satyr. It is as if Deneb is not generating its own signal, but is acting as a cosmic mirror, rebroadcasting a message it received from elsewhere. This is the concept of a natural interstellar relay. Imagine two stars separated by vast distances. If a powerful, focused beam from one star, like the Satyr signal, were to travel across space and strike the complex plasma environment surrounding another star like Deneb, that impact could theoretically excite Deneb's atmosphere. The second star would then re-emit that energy, creating an echo of the original transmission. It would be a natural, if incredibly rare, amplification system, using stars themselves as signal repeaters. The implications are profound. It suggests a universe where stellar messages can be passed from one beacon to another, creating a chain of communication across the galaxy. The haunting question, of course, is whether this relay is a random act of cosmic physics, or the signature of a technology that uses stars as its components. Are we simply witnessing a strange stellar coincidence, or are we glimpsing the architecture of a network built on a scale that dwarfs human comprehension? The Cygnus conundrums do not offer one mystery, but a relationship, a celestial call and response that hints at a universe far more interconnected than we ever dreamed. The seamless interplay of the Cygnus stars is shattered by a sound of startling brevity. The 13th signal arrives not as a lingering echo or a complex code, but as a single, brilliant chirp from the Capella system. This is a cosmic burst of energy so intense and so fleeting that it challenges the very limits of our detection. Capella, a system of two giant stars locked in a close orbit, presents a dynamic environment, but the chirp is definitively linked to the brighter, more evolved component. It is a shout compressed into an instant, a burst of radio waves that spikes to an incredible intensity and then vanishes, all within a fraction of a second. For astronomers, capturing such an event is like trying to photograph a lightning strike with a camera that takes one picture per minute. The odds are overwhelmingly against you. The vast majority of our telescopes are designed to observe long, slow cosmic processes, not these split-second eruptions. By the time the signal is registered and the observatory systems react to focus in, the chirp is already ancient history, leaving behind only a single tantalizing data point in a sea of stellar noise. This ephemeral nature is the heart of the mystery. What natural process could possibly release such a colossal amount of energy in such an impossibly short time frame? One theory suggests a magnetic reconnection event of almost unimaginable violence. Picture the star's magnetic field, a tangled web of immense power, suddenly snapping and reorganizing itself. This sudden release, focused into a tiny region, could blast out a concentrated pulse of energy, a stellar spark that flashes and dies in a cosmic eye blink. Another idea points to the possibility of a hyper-energetic impact. A small, incredibly dense object like a neutron star fragment or a massive asteroid composed of pure metal could have collided with the giant star. The resulting impact would be not an explosion, but an implosion of energy, a single, devastating crunch that converts immense kinetic force into a momentary, brilliant radio flash. The Capella chirp forces us to confront the transience of cosmic events. It reminds us that the universe is not only vast, but also fast, filled with dramas that begin and end in moments too brief for us to easily see. Each one of these fleeting signals is a potential revolution in our understanding, a secret whispered so quickly we must strain to hear it at all. That single brilliant chirp from Capella is a shout compared to our 14th signal, a transmission so faint it borders on silence. From the colossal hypergiant VY Canis Majoris, one of the largest stars known, comes not a roar but a whisper. This is an emission of breathtaking complexity, a signal woven from countless subtle frequencies that drift away from the star like cosmic dust. Detecting it at all is a triumph of modern engineering, requiring networks of radio telescopes working in perfect unison, their combined power acting as a single planet-sized ear straining to hear the universe's softest secrets. This is not a signal of raw power, but one of intricate detail, a delicate fingerprint of the star's final agony. The leading hypothesis is that we are hearing the star's last whisper, a final, complex broadcast encoded with the secrets of its demise. As a hypergiant like VY Canis Majoris nears the end, it does not die quietly. It undergoes violent, asymmetric convulsions, ejecting vast clouds of material in great heaves. The whisper could be the sound of this material itself. The complex chemical and physical interactions within these ejected shells creating a unique radio signature as they expand and cool. Each molecule, each dust grain carries a piece of the story, and their collective interaction generates this faint, multifaceted signal. It is a natural data stream, a broadcast of the star's own autopsy, detailing the elements forged in its core and the turbulent processes tearing it apart. To decode this whisper is to read the final diary of a stellar titan, a record written not in words, but in the fading language of physics and chemistry, a message meant not for us, but for the universe itself, chronicling a magnificent and violent end. From the delicate whisper of a dying hypergiant, we now encounter a storm of cosmic static. The 15th signal, originating from the star Scheat in the constellation Pegasus, is a chaotic scramble of noise, a relentless wall of radio interference that seems to defy all interpretation. For long stretches, it offers nothing but a hiss of pure randomness, the sound of a star seemingly broadcasting its own entropy. Yet buried deep within this noise are fleeting, miraculous moments of clarity. The signal will suddenly snap into focus, resolving into a brief, coherent pattern of pulses or a simple harmonic tone before dissolving back into the chaotic roar. It is as if you are listening to a radio lost between stations, and for just a few seconds, a clear, intelligible voice breaks through the static, only to be swallowed again by the noise. This erratic behavior has sparked a fierce debate. Is the noise itself the signal, a natural byproduct of a star in its ultimate death throes? A red giant like Scheat is a maelstrom of turbulent plasma and shifting magnetic fields. This constant, violent churning could easily generate the pervasive radio noise we detect, with the moments of coherence arising from rare, temporary stabilizations within the storm, like a sudden calm in the heart of a hurricane. The alternative, however, is far more provocative. Could the noise be a deliberate shroud, a form of cosmic encryption designed to hide the coherent message within? The very act of scrambling a signal is a technological concept. We do it ourselves for secure communications, masking information within noise so that only someone with the correct key can unlock it. The brief moments of clarity could be accidental leaks or perhaps even a lure, a hint of the order hidden within the chaos meant to entice a listener to try and break the code. Efforts to decrypt the Scheat scramble have so far been futile. Scientists have thrown the most advanced algorithms at it, searching for mathematical patterns or prime number sequences in the noise and analyzing the brief coherent bursts for any structure that might be a key. Yet the signal remains stubbornly opaque. This leads to a profound and unsettling question. If this is a natural phenomenon, it is one of the most complex and misleading we have ever witnessed. But if it is not, then we are faced with a transmission that does not want to be easily understood, a message from the cosmos that challenges us not just to listen but to solve it. The chaotic scramble from Scheat gives way to a beacon of startling precision. The 16th signal, the Enif enigma, arrives from the star marking the nose of the constellation Pegasus as a powerful, directional emission that appears to know we are here. This is not a broad, dissipating shout into the void. The signal from Enif varies in strength with a clear and predictable rhythm, one that syncs perfectly with the Earth's own yearly journey around the Sun. As our planet moves from one side of its orbit to the other, the signal's intensity waxes and wanes, creating a pattern that feels less like a random stellar broadcast and more like a lighthouse beam periodically sweeping across our position. The implication is as profound as it is unsettling. It suggests the signal is not being emitted equally in all directions, but is focused or aimed. This directional quality is the heart of the enigma, raising the tantalizing possibility that Enif is not just a source of noise, but a transmitter with a specific target in mind. The astronomical challenge is to explain how a star, a vast and turbulent sphere of plasma, could possibly generate such a focused and varying signal through natural means alone. One compelling natural explanation involves a colossal stellar jet. Enif is known to be a highly active star, and it may be projecting a narrow, continuous stream of energized particles from one of its poles, much like a cosmic fire hose. If the axis of this jet is tilted relative to our solar system's plane, then as Earth orbits, we would move in and out of this high-energy beam. For part of the year, we are looking directly down the barrel of the jet, receiving the full force of the signal. 6 months later, we have moved to the side, and the signal's strength drops dramatically as we only catch the fringes of the emission. This creates the exact pattern of variation we observe, a natural consequence of orbital mechanics and a stellar jet. Another theory points to a massive, warped debris disk encircling Enif. Imagine a giant, lopsided ring of dust and rock tilted at a sharp angle. The inner edge of this disk, heated by the star, could be a powerful source of radio waves. However, the disk itself would block a significant portion of this emission from certain angles. As Earth moves in its orbit, our line of sight to the star would pass through different thicknesses of this obscuring disk, acting like a slowly turning dimmer switch on the signal. We would see the signal strengthen when our view is clearest and fade when the disk obstructs it most. Both of these natural scenarios are plausible, yet they require a precise and stable stellar architecture that is itself rare and remarkable. The enduring mystery of the Enif enigma is whether this perfect celestial alignment is a mere coincidence of our vantage point, or the signature of something far more deliberate, a beacon that has found its audience across the light years. Far to the north, the constellation Perseus holds two mysteries locked in a silent celestial dance. The first is the Algol anomaly, a signal that pulses with a ghostly precision. Though it appears to come from the famous eclipsing binary star Algol, the true source is a faint, ancient red giant lurking in the same field of view. This dying star emits a series of radio pulses that are perfectly synchronized with the regular eclipses of its brilliant neighbor. Every 2 days, 20 hours, and 49 minutes, as the two stars of Algol pass in front of each other, the red giant's signal pulses in perfect time. This cosmic synchronicity is deeply strange. How can a separate, independent star know the precise orbital rhythm of a binary system light years away? It suggests an invisible connection, a gravitational or magnetic link that allows one star to feel the heartbeat of another across the void. One theory proposes a shared, ancient magnetic field, a fossilized web from the nebula that birthed both systems, still vibrating with the binary's rhythm. Another idea suggests the red giant is acting as a cosmic seismograph, its own internal vibrations subtly altered by the gentle, periodic tug of Algol's gravity, translating that distant dance into a radio pulse. The Algol anomaly presents a universe where stars are not isolated islands, but interconnected nodes whispering their secrets to one another across the light years. In stark contrast to this precise clockwork, the second Perseus puzzle offers only a constant, formless whisper. The Merfak murmur emanates from the area around the star Merfak, a low-frequency hum that blankets an immense volume of space. This is not a signal you can point to. It is a pervasive background noise like the cosmic equivalent of a room's gentle static. Its sheer scale is what baffles scientists. This murmur is not emanating from Merfak itself, but seems to fill the entire local interstellar cloud, a vast region of gas and dust through which our solar system is currently moving. The leading natural explanation points to the collective sigh of countless comets. This region of space could be teeming with trillions of icy bodies, each one slowly evaporating as it drifts through the faint warmth of the local stellar neighborhood. Individually, each comet's emission is immeasurably faint, but together, this chorus of a billion tiny whispers could combine into the diffuse, omnipresent hum we detect. It is the sound of a cosmic ecosystem, the background noise of an entire celestial environment. Yet, the uniformity of the murmur is puzzling. Why is it so constant, so evenly distributed? This has led to a more profound and unsettling hypothesis. Could this pervasive hum be a form of leakage? An advanced, galaxy-spanning civilization would require immense energy, and the waste heat from their astro-engineering on an unimaginable scale could theoretically manifest as just this kind of uniform, low-level background radiation. The Merfak murmur forces us to ask a fundamental question. Are we listening to the natural sound of a quiet cosmic neighborhood, or are we hearing the faint, unintended static of a universe that is already and thoroughly inhabited? That pervasive cosmic hum is silenced by a single, unwavering tone. The 19th signal, the Betelgeuse beacon, cuts through the stellar noise with a constancy that defies all expectation. This transmission originates from the same star, Betelgeuse, also known as Scheat, that produces the chaotic 15th signal, the Scheat scramble, yet the two could not be more different. While one is a storm of static and fleeting order, the beacon is a rock of stability, a single, pure frequency that has not wavered in its intensity or pitch for as long as we have been listening. For a massive, evolved red giant like Scheat, this is profoundly unnatural. This star is a textbook example of stellar instability, a variable star whose visible brightness fluctuates unpredictably as it convulses in its final years. Its outer layers are a turbulent sea of plasma, and its magnetic field is a tangled, shifting mess. In such an environment, a steady radio signal should be impossible. It is like finding a perfectly calm, unmoving eye in the center of a hurricane that rages on for decades. This stark contradiction is the core of the mystery. How can a star so chaotic produce a signal so serene? One theory suggests a hidden anchor, A dense, compact object like a white dwarf or a neutron star could be orbiting unseen within Scheat's expansive atmosphere. This stellar corpse would possess an immensely powerful and stable magnetic field of its own. As it plows through the red giant's outer layers, its magnetic field could act as a regulator, carving out a zone of unnatural calm within the stellar storm. In this magnetic bubble, plasma could be forced to oscillate at a single, specific frequency, generating the unwavering beacon we detect. The hidden companion would be a governor on a chaotic engine, imposing order upon the chaos. The other, more speculative explanation questions whether the star is the source at all. Could the beacon be artificial, a transmitter placed in orbit around Scheat? Its sheer power suggests it would require a staggering amount of energy that could be drawn directly from the star itself. An advanced civilization might use the unpredictable star as a perfect camouflage. Who would look for a steady, intelligent signal emanating from such a violently variable source? The beacon's constancy would then be a testament not to natural forces, but to engineering on an epic scale, a declaration of presence that persists through the stellar turmoil. The Betelgeuse beacon does not ask us to solve a code or decipher a pattern. Its mystery is its very existence, a single, stubborn note of order in a symphony of chaos, forcing us to wonder what or who is keeping the beat. That beacon of constancy is shattered by a memory of cosmic violence. SETI, the very same star we know as Mira, holds the record for the 20th and most cataclysmic signal on our list, an event so immense it dwarfs everything the star has done since. Long before we detected its erratic modern pulses, our telescopes captured a singular, historic outburst from this star, a flash of radio energy so brilliant it was orders of magnitude brighter than any other emission we have ever recorded from it. This was not a pulse or a flicker. It was a stellar scream, a detonation of energy that briefly made Mira one of the brightest radio objects in the entire sky, a title it held for just a few terrifying hours before fading back into its familiar, gentle rhythm. The sheer scale of this one-time event is what haunts astronomers. What could possibly cause a star to unleash such a colossal, singular burst of power, a fury it has never again approached? The search for a trigger has led to two dramatic possibilities. The first is a stellar merger. Imagine Mira in its distant past, gravitationally capturing a smaller, dying star like a white dwarf. The violent, final spiraling of this dense stellar corpse into Mira's expansive envelope would have been a cataclysm of almost unimaginable force. The incredible friction and energy release would have ignited a brief, hyper-luminous radio flare, a last shout from a star being consumed, explaining the unparalleled intensity of the outburst. The second theory is equally formidable, a hyperflare. This would not be a typical stellar flare, but a perfect storm of magnetic energy. Picture the star's entire magnetic field, tangled and stressed to its absolute breaking point, suddenly reconfigure itself all at once. This would not be a local snap, but a global magnetic earthquake, releasing the stored energy of millennia in one single, universe-shaking event. The aftermath of such a flare would leave the star's magnetic field permanently weakened, which could explain why Mira has never repeated such a performance. It was a one-time stellar cardiac arrest, a brief, violent death throe from which it somehow recovered. The SETI outburst stands as a permanent reminder that the universe is capable of sudden, apocalyptic violence, and that the quiet stars we see tonight may harbor the ghosts of unimaginable past fury. The deceptive simplicity of a cosmic pulse can hide the most profound secrets. Our 21st signal, the Delta Cephei deception, arrived looking like something we thought we understood completely, a pulsar. These rapidly spinning neutron stars are the universe's most reliable timekeepers, emitting radio pulses with metronomic precision. The signal from this red giant in Cepheus initially mimicked that perfect rhythm, a steady beat that seemed to confirm a dense, dead stellar core was at work. But over years of observation, a subtle, creeping truth emerged. The pulse was not perfect. It carried faint modulations, a slow, rhythmic wavering in its timing and strength that changed over periods of months and years. This was not the quick, sharp glitch of a pulsar stumbling. It was a deep, slow breath, a fundamental change in the heartbeat itself. The deception lay in its first impression, a signal that pretended to be a simple celestial clock only to reveal a far more complex and living mechanism. These slow modulations are now seen as a direct window into the star's chaotic interior. Imagine a massive bell, but one whose shape is constantly, slowly changing. As the red giant convulses and its internal structure shifts, the conditions that create the pulse also evolve. The slow changes in the signal could be tracing the migration of vast convection cells, continent-sized plumes of superheated plasma that rise and fall over long cycles, subtly altering the magnetic fields that generate the emission. Or they might reveal the gradual consumption of a planetary companion, the star's gravity slowly tearing apart a world and siphoning its material, a process that would steadily alter the environment around the star and thus the character of its broadcast. The Delta Cephei deception teaches a vital lesson in cosmic listening. The universe often presents its greatest mysteries not as shouts of the unknown, but as whispers hidden within the familiar, forcing us to listen more carefully to the rhythms we think we already understand. The rhythm of a cosmic clock can be shattered in an instant. The 20-second signal, the Zeta Aurighi zip, arrives as a frantic, stuttering burst, a series of ultra-fast pulses that seem to race against time itself. This signal originates from a unique celestial laboratory, the Zeta Aurighi system, where a brilliant red giant and a smaller, hotter star are locked in a tight, eclipsing orbit. Every few years, from our perspective, the hot companion star vanishes behind the vast, tenuous atmosphere of the red giant, and it is during this precise celestial alignment that the zip occurs. The signal is a rapid-fire sequence of radio pulses, but they are not constant. As the smaller star begins its journey behind the red giant's outer layers, the pulses start to change. They become stretched, their frequencies subtly shifting, as if the signal itself is struggling to pass through an invisible, distorting fog. This is not a malfunction. It is a revelation. The zip is being filtered through the red giant's extended corona and its powerful stellar wind, a flow of charged particles streaming off the star. Each pulse acts like a tiny sonic probe. As it travels through different densities of this turbulent outer atmosphere, it is slowed and bent, its character altered by the material it encounters. This gives astronomers an unprecedented, real-time map of a structure we could never otherwise see. It is like using a strobe light to study the intricate layers of a dense fog, watching how the light flickers and changes as it passes through. The ultra-fast nature of the zip allows us to see details on an incredibly fine scale, revealing the clumps and shocks within the stellar wind, and measuring the temperature and density of the corona with precision we never thought possible. This signal is more than a mystery. It is a key, a temporary window that opens during a brief eclipse, allowing us to decode the invisible forces shaping the final years of a giant star. A ghost follows the 23rd signal. From the star Eta Persei, we detect a primary pulse of radio energy, sharp and clear, but it is never alone. A fraction of a second later, an identical twin arrives, a perfect copy of the first signal, but fainter. This is the Eta Persei echo, a distinct time-delayed whisper that haunts every transmission. In the vacuum of space, such a phenomenon should be impossible. Energy travels in a straight line, and a single event should produce a single signal. The echo implies that the original pulse has taken a detour, that it has traveled a slightly longer path to reach us, creating that tiny but measurable delay. Astrophysicists have developed two compelling models to explain this cosmic ricochet. The first involves a circumstellar shell, a vast, hollow sphere of dust and gas that Eta Persei ejected in a previous epoch. Picture this star surrounded by its own ancient expanding bubble. When the star emits its primary pulse, most of the energy races directly toward Earth. But a small portion of that energy hits the inner surface of this colossal shell and reflects backward like a shout echoing in a spherical cavern. This reflected sound then travels across the diameter of the bubble before finally being redirected toward us, arriving at our telescopes a split second late and much diminished in strength. The echo is literally the sound of the star bouncing off its own history. The second, more exotic model points to an unseen, dense object lurking near Eta Persei, perhaps a black hole or a neutron star. The immense gravity of this dark companion would warp the fabric of space-time around it, acting as a gravitational lens. As the primary pulse travels toward us, most of its radio waves take the direct route. However, a small fraction of the signal passing close to this dense object would be bent by its gravity, forced to travel on a curved, longer path before it eventually reaches the same destination. This gravitational detour would create the delayed copy we observe. One model uses a physical wall of dust, the other a lens of pure gravity, but both seek to explain the same eerie phenomenon, a stellar signal that cannot help but repeat itself. The echo from Eta Persei is more than just a delayed copy, it is a cosmic measurement tool. By analyzing the precise timing and strength of that second pulse, we can calculate the size of the circumstellar shell or the mass of the hidden gravitational lens. We are using the echo to map the invisible architecture of a distant star system, listening to the whispers of its secrets as they bounce back to us from the dark. A ghostly echo gives way to a chorus of voices. The 24th signal, the Theta Centauri transmission, is not one sound but a dozen, a complex stack of overlapping frequencies all emanating from the same point in space. This is not a chaotic scramble of noise but a structured, layered broadcast, as if multiple radio stations were all transmitting from the same star, each on its own distinct channel. Scientists call this phenomenon signal layering, and it presents a fundamental puzzle. Is this the sound of a star conducting an internal orchestra of different physical processes, or are we hearing a sophisticated method of information encoding, a cosmic broadcast designed to carry immense amounts of data? The primary frequency is a deep, steady hum, the kind you would expect from the star's churning convective layer. Superimposed on this are sharp, intermittent spikes, the signature of violent magnetic reconnection events high in the atmosphere. Woven throughout are faint, wavering tones that drift in and out of detectability, possibly caused by shock waves traveling through the star's vast, extended corona. Listening to the Theta Centauri transmission is like standing in a rainforest, your ears picking up the steady drone of insects, the sudden calls of birds, and the rustle of leaves in the wind all at once. A natural explanation suggests we are simply hearing every layer of the star's tumultuous atmosphere at the same time, a complete acoustic portrait of its death throes. Each frequency band corresponds to a different depth, temperature, and physical process, giving us an unprecedented three-dimensional view of a stellar giant in its final act. Yet the precise separation of these layers is what fuels a more profound speculation. In human technology, we use a similar principle called multiplexing to send multiple streams of information simultaneously over a single cable or frequency. By carefully layering different signals, we maximize bandwidth and efficiency. The layered structure from Theta Centauri is eerily reminiscent of this technique. Could this be a natural coincidence, a stellar process that mimics our own communications technology by pure chance? Or does it point to a transmitter of unimaginable complexity, one that uses the star's raw energy to power a broadcast containing not one message, but many, each layer intended for a different purpose or a different recipient? The very structure of the transmission challenges us to decide if we are studying astrophysics or attempting to decode a cosmic library, one frequency layer at a time. The final signal on our list arrives from a star that was, until now, completely unremarkable. Deep in the constellation Ophiuchus, a previously anonymous red giant has begun to speak, and its voice is a chorus of every mystery we have encountered. This single transmission contains the precise repetition of Rasalgethi, the haunting harmonics of Antares, the frantic energy of the Capella chirp, and the layered complexity of Theta Centauri. It is as if the universe compiled its greatest stellar hits into one ultimate, unsolved riddle. Here we find a signal that modulates its frequency like the Gacrux glitch, pulses with the raw power of the Omicron SETI outburst, and even carries the faint, echoing whisper of a ghost, much like the Eta Persei echo. It is not merely one type of anomaly, it is a catalogue of them, all emanating from a single, seemingly ordinary point of light. This convergence is what makes it the most profound enigma of all. How can one stellar source exhibit such a bewildering array of behaviors that we have only ever witnessed in isolation across the galaxy? A natural explanation would require a perfect storm of stellar phenomena, a celestial laboratory where every possible violent and orderly process is happening at once in concert. It would need a dynamic magnetic field of impossible complexity, a hidden companion of just the right mass and orbit, a resonant atmospheric cavity of perfect stability, and a recent history of cataclysmic events, all coexisting within one aging star. The odds of such a combination are astronomically low, pushing the boundaries of what we believe is physically possible. The alternative, that this is a synthesized broadcast, a deliberate compilation designed to capture our attention, is equally staggering. It would suggest a sender who has been listening to the same cosmic whispers we have, and who understands that the true way to signal intelligence is not through simplicity, but through overwhelming, layered complexity. This final signal from Ophiuchus does not ask a single question, it asks every question at once. It stands as the ultimate culmination of our journey, a perfect mirror reflecting all the strange and beautiful contradictions of the cosmos, reminding us that the greatest mysteries are not the ones we have solved, but the ones that continue to defy every explanation. This grand cosmic puzzle has mobilized the world's greatest scientific minds and instruments in a unified quest for answers. Across the globe, a silent, coordinated hunt is underway, powered by next-generation observatories and revolutionary data analysis. The venerable Arecibo dish may be silent, but its legacy lives on through facilities like the Very Large Array in New Mexico, where 27 massive radio telescopes work in concert, their combined gaze scrutinizing the strange harmonies of Antares and the erratic bursts from Mira. Meanwhile, the immense 500-meter aperture spherical telescope, FAST in China, listens with unprecedented sensitivity, its colossal bowl tuned to catch the faintest whispers from hypergiants like Canis Majoris. These are not isolated efforts, they are nodes in a growing international network, sharing data in real time to catch these fleeting signals the moment they appear. The search extends beyond dedicated radio telescopes. Instruments like the Kepler Space Telescope's successor, TESS, monitor thousands of red giants for the subtle dimming that might betray a transiting planet or a violent ejection of material, providing crucial context for the radio mysteries. The methodology itself is evolving at a breathtaking pace. SETI, the search for extraterrestrial intelligence, is no longer just about listening for simple mathematical patterns. It now employs sophisticated machine learning algorithms that can sift through millions of radio channels simultaneously, searching for the kind of complex, layered structures found in the Theta Centauri transmission or the statistical anomalies hidden within the Scheat scramble. These artificial intelligence systems are trained to recognize not just what we think an intelligent signal might look like, but also to flag any phenomenon that simply does not fit our existing models of stellar physics. This collaborative spirit bridges disciplines, with astrophysicists, planetary scientists, and computer engineers pooling their expertise. They create complex simulations modeling the interior of a red giant to see if a Rasalgethi-like pulse can be generated naturally, or calculating the precise magnetic field configuration needed to focus a beam like the SETI signal. Every unexplained signal becomes a catalyst for new science, pushing our understanding of stellar evolution, plasma physics, and even the fundamental nature of reality. This is not a passive listening campaign. It is an active, dynamic interrogation of the cosmos, a global conversation aimed at one goal: to determine if we are hearing the chaotic symphony of nature or the first faint notes of a conversation waiting to be joined. 25 distinct and unexplained signals paint a new portrait of the cosmos. These are not random stellar noises, but a collection of precise patterns, chaotic bursts, and structured whispers, all emanating from stars in their final, most dramatic act. Each one, from Betelgeuse's erratic shout to the synthesized chorus of the Ophiuchus star, challenges a fundamental assumption we held about how stars live and die. They suggest that the final years of a red giant are not a quiet fade, but a complex and often violent language, a form of communication we are only just beginning to hear. The universe seems to be using these ancient, brilliant beacons to send us a message, written in the coded language of physics, magnetic fields, and raw energy. The greatest mystery is not any single signal, but their collective existence, a chorus of anomalies demanding we rethink our place in the cosmos. So the next time you find yourself under a clear night sky, look up at the familiar constellations. Find the fiery shoulder of Orion, the heart of the Scorpion, the eye of the Bull. Remember that these distant points of light are not static. They are dynamic, speaking, and perhaps even listening. We would love to hear which of these 25 cosmic mysteries captured your imagination the most. Was it the perfect clockwork of Rasalgethi, the layered complexity of Theta Centauri, or the ghostly echo of Eta Persei? Share your thoughts in the comments below and keep looking up. The universe is still speaking, and the next great discovery might be just one signal away.